Hi guys, this is section 10.3 where we talk about activities and activity coefficients for electrolyte solutions. Now the thing about electrolyte solutions is that their behavior becomes non-ideal at a much more dilute solution or lower concentration than non-electrolytes. And the reason is because we have charged particles in the solution, the cations and the anions. We have coulombic interactions that contribute to the non-ideality of these solutions. So they're different than non-electrolyte solutions, so we have to use a separate treatment. So we're going to start out with Gibbs energy, guys, right here, and we can write that as the moles of the solvent times the chemical potential of the solvent plus the moles of the solute times the chemical potential of the solute. Now, for an ionic compound that completely dissociates, we're going to write it this way, where this V plus and this V minus are just the subscripts in the formula. So, for example, in strontium nitride, V plus 3, V minus B2. So with that, we can now write the chemical potential of the solute as the number of cations in the formula times the chemical potential of the cation plus the number of anions in the formula times the chemical potential of the anion. And when we substitute it into our Gibbs energy formula, we get this right here. Now, thing is, we can't measure the chemical potential of a cation or an anion by itself because it's impossible to get a solution where there's only cations or only anions. It's going to be electrically neutral. So because of that, we we define something called the mean ionic chemical potential. Its symbol is the mu with a plus or minus after it, and its definition is equal to the number of cations in the formula times the chemical potential of the cation plus the number of anions in the formula times the chemical potential of the anion divided by V, which is the sum of the number of cations and anions. It's a weighted average, really, is what it is. So for the individual ions, cation and the anion, we can write their chemical potentials this way. We've been doing this for a while now. For the cation, it's the standard chemical potential plus RT, natural log of the activity of the cation, and the same thing for the anion. And this, we're going to use the Henry's law standard here because the solutions are going to be dilute. The solute will be dilute. Right? So combining these two and putting them into there's a little bit of algebra. You guys should work through it, but it's pretty straightforward. We get this formula right here for the mean chemical potential, mean ionic chemical potential. This mean ionic standard chemical potential plus RT ln of A, which is the A plus or minus, which is called the mean ionic activity. And this is what the mean ionic activity is. It comes about when you do the algebra from this. If the mean ionic activity raised to V, which remember is the number of cations plus anions, is equal to the number of the activity of the cations raised to the number of cations times the activity of the anion raised to the number of anions. Or solving this for the mean ionic activity, we get this right here. This is 1 over V. So the Vth root, I guess. Now, okay, we've come to the point where we can write mean activity coefficients for some actual compounds. So for sodium nitrate, right, V plus is 1, V minus is 1, so this would be, so V is going to be 2. So the activity of sodium nitrite squared is equal to the activity of sodium times the activity of nitrite, or the activity of sodium nitrite is the square of that product. Likewise, for aluminum sulfate, there's 2 aluminums, 3 sulfates. That means there's 5 ions, so V is 5. And we would say that the activity of the aluminum ion squared, because of that, times the activity of the sulfate ion cubed, because of that, is equal to the activity of the compound to the 5th, or the activity of the compound is the 5th root of that product. Now, it's going to be useful for us to write activities in terms of molalities, right? So we can say, we'll do it this way, just like we did with activities before. So the activity of the cation is the molality of the cation divided by the standard molality, which is just 1 molal, times the activity coefficient of the cation, and same thing for the anion. Now here, the molality of the cation is the number of the cations times the molality of the solution. So let's say it was 0.5 molal in aluminum sulfate. The molality of the cation would be 2, because there's 2 aluminums, times the molality of the solution, and so on. And our, so again, Henry's law standard once more. So plugging in, okay, this gives us this relationship here. Okay, we saw the activities already. Writing them out in terms of molalities, we get this. And again, what we're doing here, guys, is that we can't measure the activity coefficient of an individual cation or anion, so we can't do these individually. So we're going to do the same thing we just did a moment ago and define mean ionic molality and mean ionic molality coefficient. So the mean ionic molality, m plus or minus, raised to the vth power, is equal to the molality of the cation raised to the power of the number of cations times the molality of the anion raised to the power of the number of the anions. Or solving this for the mean ionic molality, it's the molality. There's a little bit of algebra in here. You guys should just use this and see, but it works out. Times the number of the cations raised to the power, number of anions raised to their power to the 1 over v. Now, activity coefficient on the mean ionic molality coefficient, this symbol right here, to the vth power is just the ionic molality coefficient for the cation raised to the number of cations. The same thing for the anion. Taking the vth root, we get the mean ionic molality coefficient is equal to the product raised to the to the 1 over vth power, to the vth root. Now we can write the mean ionic activity in terms of the mean ionic molality and the mean ionic molality coefficients. So what we're doing is we're substituting these guys up here to get this. And so we get the activity, the mean ionic activity to the vth power is equal to this, or that mean ionic activity is equal to the ratio of the mean ionic molality over 1 molal times the mean ionic molality coefficient. Now, okay, we can get, we've gotten to the point where we can write the chemical potential of an electrolyte solution in terms of its mean ionic activity. So the chemical potential of the solute is equal to the standard chemical potential of the solute plus RT ln of the mean activity to the vth power. We can also write the chemical potential of the solute as as V times the mean ionic chemical potential, which is equal to this term right here. And when we play with the log a little bit and spread it out, it ends up looking like this. And you guys should make sure that you see how we did this. What's nice about this is we can combine these first 2 terms and call that the standard mean chemical potential, I guess. It's and then these 2 terms right here, okay, break up like this. Now, what's nice about writing it this way is that everything in that, that's non-ideal is in the last term. The first 2 terms are talking about the ideal solution where the activity coefficient is 1. And so what that means is that we get all of the non-ideal behavior in 1 term right here. And we can measure the mean activity coefficient. We can measure it, different ways, with the freezing point depression, boiling point elevation, osmotic pressure. It ends up, we can also get it from measuring the cell potential for an electrochemical cell. And then, so this is a very solid, realistic way of determining how non-ideal a solute is in solution. We can also, it ends up, use a theory to calculate the mean activity coefficient in dilute solutions, which we'll do in the next section.